Alrighty, so what we're going to get through is, at the very least, parabolas, circles, and hopefully ellipses. I would love to get through hyperbolas because, again, those of you that are not juniors this year, you have to take the active placer next year. And one of the things that they do really heavily on the active placer is the conics.
Does that have to do with section 210?
I just said it's easier for people to think of absolute value as a piecewise function than it is to think of absolute value as something on the number line. So hopefully that'll make that a little easier for you. So 10.2, we're going to talk about exploring conic sections. We're going to write and graph parabolas. And a parabola is one of the many cross sections of a double mapped cone. Parabolas form a family of curves that belong to the larger family, which is known as the conic sections. So a double mapped cone, and you'll see it in the picture down here in a little bit, is like a snow cone wrapper with one facing up and another one facing down. And when we talk about cross sections, you have to remember from geometry that means that if you were to cut that double mapped cone and pull off the pieces, what would the pieces look like? What would the two-dimensional piece look like? So our essential understanding is there are 4 types of curves known as conic sections: parabolas, circles, ellipses, and hyperbolas. Each curve has its own distinct shape and properties. And the thing that's going to help you hugely with parabolas is that these are the ones we have spent all of our time on up until now. Y equals ax squared plus bx plus c. And all of our parabolas opened up or down. So when you have y equals x squared, that tells you you're going to have a parabola that opens up or down. Now, how did we know if it was going to open down?
Negative.
If there was a negative in front. Exactly. So just knowing, hey, we've already studied these a lot. If it's y equals and then our a value is positive, it's going to open up. If it's y equals and then we have a negative a value and an x squared, then it's going to open down. So when we get to these, you know something's up. And that's because the y equals x squared, we're up and down. And now if we see x equals y squared, we have to think, okay, that's different. That's not something that I learned in the past. These are going to be our right and left opening parabolas. Which always brings us to the, okay, so how do we get them to turn? I mean, we know the up and down ones, we've been studying those forever. And now we figure out that if it's x equals y squared, that's going to be right and left. But what if we need to turn them? Well, that requires trigonometry to make those angles happen. So we're not going to study that deep right now. We're just going to look at some real basic stuff. So these are our conic sections. And you can see, and especially with color, not as good as in the packet, the packet's just a black piece there, but you can see how when they cut these out, they're showing us the different cross sections that you could get when that happens. And those cross sections are what we study from the double mapped cone. And here we would see a circle. That one's perfectly parallel to the base of this double mapped cone. Here they're showing how we could get a parabolic shape if we cut that out. And this piece, it's not a perfect circle because it has been off balance, off center. That makes it an ellipse. Layman's terms, it would be called an oval. I mean, that's what it is, but we call it an ellipse. And then because this hits in 2 different spots and it forms basically 2 nice and symmetric parabolas, those are called hyperbolas. And like I said, I wish we could get that far, but I just don't think it's going to happen because we want enough time to study for the final, of course. So, essential understanding. Each point of a parabola is equidistant from a point called the focus and a line called the directrix. So this is a big step for us. Before, when we give you parabolas, we just said, here they are, find some good points and tell us where this is going to be graphed. And we didn't have any idea why parabolas formed the way that they did. So what they're telling us here is, there's this magical little point called a focus and a line behind it that's called a directrix. Now, we get a parabola, and what's going to happen is it's going to wrap around its focus. But there's a line behind it that is called a says wrong way. That's what a directrix does. It's like a wrong way sign. Don't go this way, go the other way. So my parabola is supposed to be going to the right. My directrix is going to be back here saying don't go this way. This is the wrong way. Go the other direction. Now it's the distance from the directrix to the parabola to the focus that we're interested in. It says that each point on the parabola is equidistant. So there's a geometry term coming back to us there. From a point called the focus and a line called the directrix. So the distance from here to here, and granted I'm not drawing this to scale, is going to end up being the same as the distance from the parabola to the focus. And that's what makes it form. Because for every point that there is on that parabola, that will be true. And they're going to have a little better sketch than this on the next page here. So we could see, here's that directrix, that line that's giving directions and saying don't go this way, go the other way. They use color, but that is a helper line, so technically it really should be dashed. You should make your directrix solid. And that's going to be behind the graph saying, don't go here, go that way. But the focus is always what that parabola is wrapping around. And with the parabolas we're going to study, they're always going to be nice and symmetric. So we'll have an axis of symmetry that will go through there. And the same thing when we have our horizontal parabolas, our right and left opening parabolas. So the vertical ones, y equals x squared that you covered before, this is that. But x equals y squared is going to be the horizontal parabolas over here. So a parabola is a set of all points in a plane that are the same distance from a fixed line called the directrix and a fixed point, not on the line, which is called the focus. The fixed point, focus of the parabola, fixed line, the directrix. Now the distance between the vertex and the focus is called the focal length of the parabola. That just sounds difficult. We're going to find out that in these equations, we're going to have this piece called 4p. 4 shows up in parabolic equations. It just does all the time. Now 4p is called the focal width. And that focal width is related to, of course, how wide the parabola is at the focus. But p, that's sometimes what we have to find, that lowercase p. And what that is the distance from the focus to the vertex. Or distance from vertex to the focus. Now when we get to pre-calculus, it's going to call it the directed distance from the vertex to the focus. That directed distance tells us, hey, you might have to throw a negative in there. I mean, if it's opening up and it's opening right, that's a positive value, but if this is going to open down or to the left, then you'll have to make sure that this is a negative value. So that's the one we're going to need if you want to write equations for parabolas, that little distance from the vertex to the focus. We're going to study horizontal and vertical parabolas. All vertical parabolas have a vertical axis of symmetry, just makes sense. If you're going to open up and down, then your axis of symmetry is going to be x equals something, so that you have that same thing folded over on either side, symmetry. And then all horizontal parabolas will have a horizontal axis of symmetry and a vertical directrix. So things flip-flop. Horizontals, y equals something. I'm trying to figure out what that axis of symmetry is. And like I said, they do a much better job down here. This picture for us to show us, yes, the distance from the directrix to a point on the parabola is the same as the distance to the focus. And that's anywhere on the parabola, not just one specific point. The distance from each point on the parabola to both the focus and the directrix is the same. They're equidistant. So that's how they form. And like I said, if we want to write them, what we're interested in doing is telling people how far is it from the focus to the vertex. That's our p-value. And again, if it opens left or down, we have to make sure we put a negative on the equation so people will know, hey, it's going in this direction. And we'll start by just looking at some basic, hey, how do we get these graphed? Not by using tables, not by using any of the stuff that we've known in the past, but that's because parabolas can come in tons of different forms. And like it says, P is the distance from the vertex to the focus, and 4P is called the focal width. And I actually added that. This book doesn't get into focal width, but in pre-calculus, we use that all the time because it's a really quick and easy way to graph parabolas without having to make a table. And if we don't need tables, we don't want to use them. So problem number 1 says parabolas with equations x squared equals 4py. All right, now, if x squared equals 4py, what I'm looking at first is, it really is saying y equals something x squared. So what I need here is to know that this is going to be up or down. And really the way that you catch it as you go through algebra or pre-calculus is, they're not both squared. I mean, that's huge. Only one of them is squared, and the one that's squared is the x squared. And that means this is going to be an up or down opening parabola. And it wants to know what is the equation of the parabola with a vertex at the origin and a focus of 0, 2. Okay. Well, if x squared equals 4py, it looks like the only thing I have to figure out is, remember, x squared and y are supposed to stay there. They're part of the equation. So I just need to know how far is it from the vertex to the focus. Well, the vertex is at the origin, and the focus is at 0, 2. And parabolas wrap around their focus. And I'm doing that dash because I don't know if that's exactly what the parabola looks like. I just want to get an idea of what's going on, and I see, well, this one is, it's opening up. That's what's going to happen here. So if it's up, I don't need a negative. All I need to do is be able to count from the vertex to 0, 2. And that's 2. So if P is 2, x squared is going to equal 4 times 2. Y. X squared equals 8y. That's done. So do I have to finish the graph? No, I don't have to. But I want to show you how easy it would be to do that. This 4p value right here, the 4 times 2 that we just got as we went through this, that's called the focal width. That tells us how wide this parabola is at its focus. So if this is an 8, or 4 times 2, that means we need to go 4 units to the right and 4 units to the left from the focus. 1, 2, 3, 4. 1, 2, 3, 4. And there's a nice little sketch of our parabola without making any tables. And then, of course, I know that the directrix is going to be here. It's going to be equal but opposite to where the focus is. And it's going to say, don't go this way, go the other way. So my directrix would actually be 2 units down at the line y equals -2. Right there. And then I would have all the pieces that I can do for this parabola. So parabolas are not difficult. It's just that when you're back in exponential, it just takes too long to show you all the pieces where this comes together. So this one says, what are the focus and directrix of the parabola with the equation y equals -112 x squared? And I noticed with the other one, it was x squared equals something, and this one's not x squared. So I want that nice little 4py equals x squared look. That means I have to figure out how to get that -112 over the other side. Pardon the other side. How do you do that? How do you move that -112 over? Multiply by the reciprocal. Multiply by -12. So -12y equals x squared. Now, how do I know this is centered at 0, 0? There's no h and k stuff going on. I mean, if there's going to be an h and a k, it's going to be, the h will be connected to the x, and the k would be connected to the y. There's nothing there. So this one has x squared, which tells me up or down. What does this tell me? And that means it's going to open down. So we've got a little 0, 0, and 0, negative 3. And then I'd like to use the focal width to just get a nice little graph real quick of this thing. And that means I need to know, okay, what's going on here? Now, 4p, notice it didn't have a negative on it. And that's because we don't care whether or not it's positive or negative. What we want to know is what's the distance that we're talking about here. And that's going to be 12 units. So this needs to go 6 units out from the focus on either side. Like so. And then the directrix is going to be equal but opposite behind the vertex, the same distance that the focus was. So if this is 3, 1, 2, 3, there's our directrix right there. And their specific questions were, what are the focus? Well, the focus is 0, negative 3. And then the directrix. And the directrix is going to be the line y equals 3. Again, the great thing about using that focal width is that we're not going to have to find any points on the graph. We can generally get a really good sketch of it without having to do all of that. So far, so good? Okay.
How neat is that?
So, skip these and get to some of the other good stuff about this, because you guys have done up and down parabolas your whole life now. Probably better get to the other ones. So let's shoot past this and start talking about those that are y squared equals 4px. So these are your right and left opening. Again, the difference is which one's being squared. Up and down is x squared, right and left is going to be y squared, but they follow all the exact same principles. You have a focus inside the parabola, the directrix is equal but opposite on the back of it, saying don't go this way, go the other way, and the focal width is still going to be right here. There's the focus. How far is it to the parabola? And then they use that entire width. So what we do, it really is just bring it in and use that graph as we go through. So here it says, let's look at some parabolas with the equation y squared equals 4px. What is an equation of a parabola with vertex at the origin? So that means it's pretty standard stuff. And the directrix of x equals 1.25. Like that. I'm going to change that into 1 and 25/100ths. Which is 1 1/4, which is 5/4. Now think about the equation that we're going to use. Why would that be advantageous? Use that. What is it in our formula that's going to make that work out nice? The 4p. Yeah. So if we can change this decimal business into fractions, it'll go pretty quick. So our little equation is supposed to be y squared equals 4px. But it said the directrix is x equals 1.25. So x equals 1.25 right here. What does that mean for my parabola? If its vertex is right here, and the directrix is the line that says don't go this way, go the other way. Which way is this open? It's got to go left, which means we have to be careful because we're going to need a negative. So basically that drawing is to get us to figure out, hey, this is going to require the use of a negative because we need this to be left. But we've got x equals 5/4 sitting right there for the directrix. We know that the focus is equal but opposite on the other side. So the focus is going to be back here at negative 1.25, which is negative 5/4. So if I just put negative 5/4 into b, I should have this. The 4's are going to cancel out. And y squared equals negative 5x. Now if we were to graph this this one. We wouldn't be too happy about this being a -5. But it's still a 4p, and we could do it if we had to. But this didn't say we had to graph it. It just said we had to figure out, what is this going to be for the equation? And for the equation, it's going to be y squared. Y squared equals -5x. So this one, what are the vertex, focus, and directrix of the parabola with this little equation? And again, I'm going to change that into a fraction. Looks like that. So I think, okay, if it looks like that, how did it get there? Well, it's supposed to be x equals 4py squared. No, the squared is always by itself. So it should be y squared equals 4px. So how do I move that 3/4 over to the other side? Multiply by the reciprocal. Looks like so. Okay. Well, here's what I know. This has to give me 4p. Has to. So how do I find p, which is that distance from the vertex to the focus? Divide by 4? Yeah, it's a fraction. You might want to even think, hey, let's go ahead and multiply both sides by 1/4. 4's will cancel. P is 1/3. All right, so now we're supposed to find the focus, the vertex, and the directrix, all from that, huh? Well, the vertex is easy. It's 0, 0. There isn't any HK business going on here. So vertex at 0, 0. But the next piece is, what's going on with this? Is this up and down? Is it right and left? And then be more specific. Is it supposed to be just right? Is it supposed to be just left? Where is this parabola going to go? Has to go to the right. Y squared is right and left. We don't see any negatives in here, so it's going to go to the right. So here's our vertex. And then we figure out, okay, well, P was 1/3. This is going to be really, really close here. There's our little focus right there. So our little focus, yeah, it's really close. I'm sure you guys' paper got really, really tiny.
Yeah.
So where's the directrix then? Super duper close back this way.
Y equals, I should have broken the x.
Yes. X equals
Yeah.
-1/3. Yeah, because again, it's
I was
right
thinking-
up. And this one too, this would just be a mess to try to graph with 4p equaling 4/3. They didn't ask us to graph, and the ones that they do ask us to graph, they're going to give us nice numbers for that, so that we get used to using this process as we go through it. All right, let's see. So let's go here.
Well done.
Why even bother studying all of these conic sections? They have a lot of uses. The geometry of a parabola implies a very important reflective property that gives real-world meaning to the word focus. If you ever see a dish for somebody's television or whatever it is that they have, they are in the form of a three-dimensional parabola. And that's because what happens is, as something hits, whether or not it's sound waves, radio waves, whatever it is, hits the parabola, it bounces off the sides and it shoots towards the focus. And that's what amplifies the sound, the picture, everything that's going on there. So what you see here are the sounds, sound waves, the radio waves, everything else that hits this dish. And when it hits, it bounces off to the focus. And that's where it's going to collect all that good information and put it back together again. So as the diagram of the parabolic reflector shows, lines from the focus reflect off the parabola along lines parallel to the axis of symmetry. This is how a flashlight works. Looking backwards, you've got that bulb in the center and focus, and it hits outside of the parabola and projects forwards. Conversely, lines parallel to the axis of symmetry reflect off the parabola directly into the focus, and that's how that satellite dish works. So they use the properties of this parabolic figure to get an intensity that they want. It's like, well, I'm sure you guys have had your TV go out when there's a storm before. Because what's happening is some of those signals are not making it there. Some of them are, but some of them aren't because of the rain and lightning and those types of things. So it's grabbing as many signals as it can, but it's not getting those into that focus enough to where you can see the entire picture. So that's what they try to do. So down here we have a little solar reflector. The parabolic solar reflector pictured has a depth of 2 feet, and then it says it has that depth of 2 feet at the center. How far from the vertex is the focus? What is the focal length? So what we would want to do is place the Cartesian coordinate plane in a place that would make it easy for us to write an equation for this, and that would be having the vertex at 0, 0. That would be the absolute easiest thing we could do. So I look at this and I think, all right, they told me this depth right here is 2 feet. And since it's 8 feet all the way across, this must have been 4 feet. Well, if that's the case, I know a point that's on this parabola because I go 4 to the right and 2 up. This is 4, 2. And then I think, okay, this one opens up. So should I use x squared or should I use y squared? X squared. I don't know what p is yet, but here's what I do know. I have a nice little x and y I can use over here. And if I have x and y in that equation, the only thing that's left is p, and I can find it by putting that in there. So if I put my 4 in for the x, and I put my 2 in for the y, this will say 16 equals 8p. These two. And that's what they wanted to know. How far from the vertex is the focus? 2 feet. So we use the information that they give us to figure out what is p in this, you know. And if we had an actual coordinate plane right here, we could see exactly where that stuff is. But if we don't know, we could put in the x's and y's, and we can find it because that's how the equation is built. It's to give you all of the points that are on that parabola. Now, I'm going to have you guys talk me through this one a little bit. This one says the mirrored reflector of a flashlight is 8 centimeters across and 4 centimeters deep. All right, so here we go. Where should we put our 0, 0? At the vertex, yeah, this lowest point right here. Now, if you're saying, well, if it's a flashlight, maybe we should go right and left. It doesn't matter. They didn't tell us which way to go. So we can do it either way. All right, so here's our 0, 0. 8 centimeters across. So I should use a 4. 4 centimeters deep. What do I use that for? The y value. We got a lot of 4s going on here. So what ordered pair would represent that little blue point? 4 and 4. Now I went ahead and made this one. I squared again. Wouldn't have to. It'll work with y squared equals 4py as well. And then I need to put in my numbers for x and y. So how far from the vertex should the light bulb be positioned? 1 centimeter. Very, very nice. Well, it's got to get a little harder than that, right? Here's the deal. If we translate these, we're going to deal with some H and K business. You studied how to translate a parabola from one vertex 0, 0 to one with vertex HK. We did that earlier this year. For such a translation, all the other features, axis of symmetry, focus, and directrix, translate along with the parabola and its vertex. So what happens? have this. And then we see, well, if there's an H, a horizontal shift, it has to be attached to the X. And if there's a K, it has to be attached to the Y. So this would be an up and down opening parabola that's been shifted H and K units. Now, if you look at this box, this is the only book I've ever seen that does this. They made this way too complicated. So what I've been going through and teaching you is actually stuff from our pre-calculus book and our college algebra book. For some reason, this book wants to use 1/4C to talk about the focus. And that is just a total mistake. It just makes it much, much tougher. So ignore their 1/4C business. And just think about the 4P and having the X squared or the Y squared all by itself. So if we do this for our Y squared, it would look like that. So we're translating these right and left. And like I said, I don't necessarily use this paper a whole lot. Think about what we were doing, it'll go a lot easier. So now, what's going to be a big change? We really have to think of how P is the distance, the directed distance from the vertex to the focus. Because it's not going to be so plain and easy as it was before when we have an H and a K. So problem 4 says we're going to analyze a parabola, and I look at it and I think to myself, that doesn't look like any of the stuff we were just doing. And that's because we have to complete the square. You guys remember completing the square? We need to make this look like this and this. So we have to complete the square. So let's see what happens. All right. Y equals x squared minus 4x plus 8. Is 8 a perfect square? Am I running out of time?
Yeah. No, you've got plenty of time. Keep going.
How close am I?
Yeah! Oh, I was.
You guys should stay quiet.
That means we're
Gonna
going to
tell
cut off
her
some
ring and she
problems.
wasn't gonna give us.
Oh, I'll give you homework.
I think what we should do is put up 30 to 59.
That's actually
That's pretty reasonable.
That's pretty reasonable.
Go on. That just means 7 through 21 odd. That's pretty reasonable.
It is. Great deal.
Rats. That might take, I wonder, because we haven't taught this before, whether
Yeah.
I might have to take 2 days on this, but that means no ellipses, and that stinks.
Oh, you will. Whatever show we do. I guess we'll do that for next. We have 2 right now. Oh, don't worry. I have the thing right now. I have no idea what's going on. Like, yep.
Oh, stop it.
No, I'm not even kidding.
Stop.
No,
Yes!
ah,
Bro, I'm not even kidding.
I knew it. I was looking at
Bro,
I
I'm
think we
not
should
even
just cut it
kidding.
into a sentence.
What you can do.
Well, this is just fine. This is about how much every day is equal.
We have an advisory schedule today.
That means I can work on it Friday.